Welcome to Lecture Online, and now we're going to talk about the crystal structure of atoms when they're in a solid state. So now we're taking a look at the solid portion of chemistry here, and what we'll find out is that when atoms and ions and molecules come together and set themselves up in a solid state so that they're hooked together and they don't move relative to each other, well, they may vibrate, of course, through thermal action, but they're no longer moving relative to each other, they're staying put in place. We can try to figure out what the structure of those atoms and those ions are. Now, we're going to run through different types of structures. One of the most common one is what we'd call the simple cubic structure, and there's different types of atom and ion build-up, so to speak, within those structures, but the general structure is that they're cubic in shape. There's perfect symmetry in such a way that the width, the length, and the height of the cube is exactly the same. For example, A equals B equals C. So let's go ahead and write that. A equals B equals C, so I have a simple cubic structure. And also that the angles are all 90-degree angles. So the faces relative to each other are at 90 degrees from each other. So we can say that the angle alpha is equal to the angle beta, is equal to the angle gamma, is equal to 90 degrees. So we have a perfect cubic structure. And so, for example, atoms may be packed together like this. And the way we draw the cubic structure is by putting the corners of the cube at the center of the atoms in such a way that no matter where you put this cube, the content of the cube will be exactly the same. So if we draw another cube right next to it with four more of these atoms there, you can see that the next cube will look exactly the same as this cube, will look exactly the same as the one to the left, to the top, to the bottom, to the front, to the back, and so forth. Now, of course, not always are the ions the same shape. Most of the time, they're not. They're different shape. And so there may be a slight different way in which the atoms are arranged. For example, in sodium chloride, the chlorine atom, the chlorine ion is much bigger than the sodium ion, so they tend to pack slightly differently. It's still a cubic shape, but you can see in order to draw what we would call the unit cell, the cell that represents the same everywhere within the structure, has to be drawn a little bit differently. It has to be drawn from the center of the large chlorine ion to the center of the large chlorine ion. When you find it again, with the sodium ion in between, notice you'll have a big chlorine ion in here, chlorine there, chlorine there. So the unit structure here is a little bit different than it is there. But again, if you take this cube and you place it over here, you'll have the exact same contents of that crystalline structure over there. So that's the concept of the unit cell. So what we're going to do in the next so many videos, we're going to try and figure out what is exactly contained within each unit cell, depending upon what the crystalline structure is, what the atoms and ions are involved in the crystalline structure. Try to figure out how much of each atom within the structure is part of the unit cell. For example, how much of this particular atom is part of this particular unit cell? And so you may say, well, isn't the whole atom part or the whole ion part of that cell? No, that's not exactly true, because what we're doing here is putting the corner right at the center of that atom. Of course, in reality, it's more like this rather than this, but sometimes it's easier to see when we draw it out like that. Now imagine there's going to be a cube in the front, there's going to be a cube on top, to the side, and to the bottom right here, and it's going to be underneath, to the left, to the right, and so forth, in such a way that each of these atoms at each corner is really shared by 8 of these unit cells. Only 1/8 of the atom belongs to this particular unit cell. The other 7/8 belong to the other 7 unit cells that would be adjacent, encompassing part of this particular atom like that. So you can imagine if you draw another one like here, you go straight out this way, you can see that now that this atom is shared between this one, this cell and this cell. If you then draw one in the front this way, in the front that way, you can see that this atom is also shared in the unit cell over here and the unit cell over there. So now you have 4 unit cells here, and so only half the atom belongs to those 4 unit cells. The other half of the atom would be sticking above those 4 unit cells. So if you then place on top of that another 4 of these unit cells, that half of the atom would then be subdivided between those 4 cells right above it in such a way that 1/8 of this atom belongs to each of the 8 cubes or unit cells encompassing that particular region. So how much of the atoms are then inside any one of these unit cells? In the case of an arrangement like this, 1/8 of this atom would be in the cell, 1/8 of that one, 1/8 of this one, 1/8 of this one, 1/8 of that one, 1/8, 1/8, and then of course there's one in the back here which I didn't draw. If I were to draw that, it would kind of like sit in the back like this, around the corner in the back of the cube. And so you can see there's a total of 8 of those atoms, each of them donating or encompassing 1/8 of that atom within that unit cell. So this particular arrangement of atoms or ions would only have 1 atom within that particular unit cell. As you will see, when we start looking at things such as sodium chloride, which is a little bit more complicated, it's a different way in which you want to count how much of each atom belongs to that unit cell, and how you then can find out how many atoms are contained within that unit cell. In a later video, I'll show you how to do that. One thing to keep in mind is that it's important to figure out the size of these unit cells as well. Now, for example, with sodium chloride, notice that the radius of the chlorine ion is about 181 picometers. The radius of the sodium ion is about 95 picometers. So how big is that unit cell? Well, through X-ray diffraction techniques, we discovered that the unit cell has a side of 564 picometers. Now, if you imagine for a moment that you would have to take the full diameter of the sodium ion and half a diameter or a radius of this chlorine ion and a radius of that chlorine ion and add it all together, what would that add up then up to? So here we have 181 picometers for this one, plus twice 95, plus 2 times 95 picometers, plus then again 181 picometers from that one. And let's see, I have a calculator right here. Let's take a quick check here. 181 times 2 plus 95 times 2 equals, that would be a total of 552 picometers. So from simple calculation and knowing the average size of these ions, you would expect the unit cell in this case to be 552 picometers on each side. In actuality, it's a little bit more. It's 564 picometers. So why the difference? Well, it turns out that these are average values for the radii of these particular ions. Depending upon what they're mixed with, that radii can change. That, of course, it involves electrical forces, and so sometimes they're squeezed a little bit closer together, sometimes they're repelled out a little bit further out. And in the case of the sodium chloride, notice that the close proximity of the chlorine ions probably pushing these ions a little bit further apart so that the unit cell has a side distance or length of 564 picometers rather than what we would expect to be 552. But it's in pretty close agreement. So that's the basics of the unit cell in the crystal structure of atoms in the solid state. And now we're going to systematically look at the various types of crystal structures that can exist and the various ways in which atoms are packed within those crystal structures. And from that we can calculate densities and so forth. And that's a pretty neat thing. So stay tuned, take a look at the other videos if you're interested in this kind of stuff.